First thing Nadia asked, what do you mean by language? And so the first thing, Brandy was asking me to come up with a title a week ago, or 2 weeks ago, and I dragged my heels, and this is the title I came up with. And there was work on the language side I wanted to talk about that for the sake of not going on and on and on, I'm going to cut back. So there's a slight modification to what I mean by language. And it's not quite language, it's language-ish. So I'll talk about a little bit of work that relates to language. If anyone knows, George Santo was Jew-ish. So that's where this comes from. Okay, so this work is really, and I should say that some of these slides works out. Zidane Wang is a student at Northwestern. She was giving an exam presentation, so she was making slides. So I was fortunate enough to have her send me her slides. So thanks to Zidane for some of these. This is joint work with a bunch of people that are at, Takaru Obo, who is at TTIC. He visited for about 4 or 5 months. Bradley, who was an RAP here, is now at Northwestern. His student Zidane. Lucha Aga, who was at UChicago way back when, and now is at MIT. Takuma and David. So this is going to be about learning from demonstrations and, as I said, language-ish. So what's the motivation? So we want to take as input. We want a robot to be able to perform some tasks. Maybe I want a robot, I like coffee, it's tea, but I like coffee. Maybe I want to be able to send my robot downstairs and have it make me an espresso. So that's hard, right? It's easy for people, but that's really challenging for robots. They're okay at picking and placing things, but that's about it. But maybe I could teach them to make me a coffee. So what I might do is I might give them demonstrations. I'm an expert. I've made a lot of coffee. So I'll show a robot how to make a coffee. So I'll do that. So look at this video, okay? So now I want the robot to mimic this. And so how might we do this? So I have this observation here of this state, in this case, images, this image sequence. And I might have some actions, right? So I might say the action space is this stitched-off pose of the cup over time, right? And so now I can do that with the robot with its end effector, have it trace the same trajectory. And so now what I get is I get these state action pairs. When the cup was here, here's the action that the user took. They moved it towards the espresso machine. And then the next time step, I get another image, and I have the corresponding action that the user took. And so now what I might do is I might use these state action pairs and have a robot learn a policy that emulates this. So I might have this is Sawyer, we have our Baxter downstairs, and I might ask it to mimic the expert, to reproduce this procedure. Okay. So what I want to do is I want to learn a policy, some function, that maps states to actions. In this case, the states are our observations. The actions, again, are maybe velocity of the end effector, velocity of the robot's hand. And so the question is now, what I'll talk about is how might we go about learning a policy from experts? And so just an outline of the talk. Just, again, I'll give a brief introduction to imitation learning, and I'll talk about one approach that we've taken and others have taken to imitation learning using generative models, particularly diffusion models. And I'll talk about diffusion models for imitation learning, diffusion models for shared autonomy, and then the last bit, what do we do when the demonstrations are not from experts? They're suboptimal. So just a brief introduction to imitation learning, so in a nutshell. So what we're given, and we'll assume at least for the first 3/4, 4/5 of the talk, is that we're given demonstrations of desired behavior. So say we're not making coffee anymore. I want to make a self-driving car. I want to play Mario Kart, right? And so I want to be able to teach my car to drive, or I want someone to be able to teach my car to drive. And so what I'll do is I'll drive around. Tesla basically is doing this now. They're crowdsourcing this. I'm going to get a bunch of demonstrations of hopefully experts, driving. So emulating some desired behavior. So that's the input. Large data set of data of these demonstrations. And my goal is to learn this policy that maps states, images in this case, to actions. And so what do I need for that? I need my demonstrations, so paths and some racetrack. My state action pairs that I'll get from this. I need some learning model, some representation of the policy. And then I need some loss function. I need to be able to compare the demonstrations to what my policy is output, and come up with a loss that allows me to emulate this desired behavior from the user. Okay, so I've already talked about what we might formulate this, but we're going to formulate this as maybe an MVP, some Markov decision process, perhaps, or just generally a collection of state action pairs. So we have our states, they may be partially observed, we have an image, we don't know exactly where everything is in in the environment, particularly things outside the field of view. We have our action space, steering, gas, brake. We have some environment dynamics, and we want to learn this policy. And this policy might be deterministic. Given this image, turn 5.5 degrees, or it might be stochastic. 80% of the time you should turn 5.5 degrees, but sometimes you should turn 10%, right? So we're going to assume access to demonstrations. Each demonstration is a trajectory. It's a sequence of state action pairs, starting from time 0 to some final end of the episode, capital T, for a fixed length. And so what we assume is that these actions correspond to draws from this expert policy. We'll call it pi star. That's the policy, the latent policy that this expert or these experts are executing. And sometimes the trajectories will include rewards, not in this talk, but sometimes people formulate it that way. Sometimes it won't include actions. Maybe in this domain, actually I don't know where the cup is. I really just have an image sequence. I don't actually know the position of the user's hand or their velocity. Okay. And so from this, I can get two distributions. I can get a distribution over trajectories under some policy, and we'll represent that as p sub pi or tau, or a distribution over states. Okay. So now, as I mentioned, with this, we have these demonstrations. We have some model class for our policy. It's more than likely going to be a neural network. And now I want to learn a policy. What do I need? I need my objective, or it's an objective, my loss. So I want this policy to behave similarly to these experts. What do I mean by similarly? And there are various approaches you can take to this. I don't want to say standard, but one of the oldest approaches is to treat this as a classification problem. So I have a set of discrete actions. My action space is discrete. I have demonstrations. Well, in this state, user chose action 10, and this other state is action 5. Now I can treat this as a classification problem. So I can use various classification losses. Maybe my action space is continuous. I treat this as a regression problem. I might treat this as an inverse RL problem, where if you're familiar with RL, what I'm going to assume is that there's some latent reward that this expert is optimizing, but latent, I don't know it. From these demonstrations, I'm going to intuit or infer the reward, and then now I have an RL problem that I can solve. Another way you might formulate this is as a distribution matching problem. I might want to match from these demonstrations. That gives me samples from these distribution over trajectories, or distribution over states, or distribution over actions conditioned on states. And that's what my policy is. So I might want to learn a policy that matches this distribution under some F divergence measure, like Kale divergence. Okay, so Kale divergence. In animation. Okay, but let's look at very quickly. Let's look at one form of Kale divergence. So we have two distributions. These are distributions over trajectories. One under the expert, that's p of pi star, and then one over the learner, p of pi tau. And we're going to formulate this, and again, it's not really the math is not terribly important. But if you formulate this objective, you come up with we want to minimize this divergence measure. That means that these distributions are going to be more similar. This corresponds, if you've taken the graphical models class, what's referred to, or what's known as the M projection. This is the exact objective of the oldest or one of the most widely used approaches to imitation learning, which is behavior cloning. Really treating this as a supervised learning problem, where we want to match we want to match the actions predicted by the expert. So with cross entropy loss, this is exactly what we get. Okay. So how might we do that? With behavioral cloning. Again, we want to learn this policy that matches demonstrations. So I'm going to collect these expert demonstrations, have people drive the car, a bunch of experts, race car drivers drive the car, get these state action pairs. I'm going to compose a data set. This data set really is just a collection of state action pairs. I'm going to throw out the fact that they're taken along a trajectory. I just have this bag of state action pairs. And I'm going to train my policy to minimize some loss, cross entropy. Now, there's some issues with behavioral cloning. One is that the data that I'm getting is exogenous to the learner. So it's collected by some expert. The learner does not affect the states that are visited. So what that means is that, as a result, behavioral cloning tends to be sensitive to distribution shift. So if I have an expert driving, the expert is always probably going to stay down the center of the lane. If, for example, the learner finds itself off the road, it's never seen that state before because the expert never goes off the road. They're always doing a good job driving. Now the question is, what do we do? What does the agent do? And I said this has been used for a long time. So some of you might be familiar with Alvin. I think the citation for behavioral cloning out of CMU. They have NavLab, and this was the NavLab 2, where they had this Humvee vehicle using a neural network, so taking as input, in this case, an image, a pretty small, low-resolution image, 30 by 32. I think from the paper they were just using the blue channel, so it was color, but they were just using blue channel. Some of the network would take as input a laser rangefinder, and then the output is steering directions. So where should the agent steer? And they've trained this in a variety of ways, doing sim-to-real transfer. So they would train it on a data set of 1,200 simulated images. And they go about half a meter a second.
What year is this?
88, I believe.
Yeah.
Does it say here?
It's from 88.
Yeah, 88. Yeah. And then there's this video, actually, this video plays. There should be audio. So Chuck Thorpe at CMU, I think, was one of the, Avra might know, but I think the founders of the NavLab. So they got up to 50 miles per hour, and where they would collect, now you would drive for 5 minutes, and then it could switch over to autonomous driving, steering down the road. So pretty impressive. But again, this is basically behavioral cloning. Another problem with behavioral cloning, in addition to what I mentioned before, is that a problem with the M project. Well, let's say that your expert distribution is this black curve here. So you have this bimodal distribution. Sometimes the expert likes going, or the experts sometimes go to the left, sometimes they go to the right. If I'm going to find, behavioral cloning minimizes this M projection. And what that corresponds to is fitting, in this case, this Gaussian distribution that sort of takes the average of these two. So that's this red distribution here. So what this is going to do is this is actually going to place a large amount of density on actions that the expert actually wouldn't pick, and lower density on actions that really have high likelihood under the expert. So what does that mean? Say you're driving around and there is this fork in the road. This is from the Muppet movie. Literal fork in the road. And so the user's going to go to the left or the right. That's this bimodal distribution. Now my behavioral cloning policy is going to say, I'm going to drive straight and hit this cone or hit this fork. Okay. So how might we do that? One approach is, let's do distribution. Right? Let's try to learn this distribution. So can we do that with a generative model? And particularly, let's look at a diffusion model. So I'll speed through this, but a quick intro to diffusion models. We have some underlying data distribution. This is a distribution over images of dogs. Right? And what we'd like to be able to do is I'd like to be able to synthesize my own image of dogs. Not personally, but maybe some people like dogs. And so they want pictures of dogs. So I want to learn this distribution. And with some model class. And then what I want to do is and then what it's going to allow me to do by drawing from this distribution, I can render images of dogs. And I'm sure everyone here has seen various diffusion models for images, now lately for videos, producing these TikTok-like dance videos. I don't know why that's a big thing, but I guess people like watching people dance on TikTok. And so diffusion models, it's this not-so-new generative model. Like a lot of models, it's inspired by statistical physics. And again, the basic gist of this is we're going to generate this Markov chain. And I have some distribution over the data queue. This is my distribution over images of dogs. And I'm going to generate this distribution, right, my model, using with my model, or emulate that distribution, by learning to take this distribution, add a lot of noise, I'm going to destroy structure in the data set, and then learn to reconstruct it. And the way that I'm going to do that is through two steps. This forward diffusion step, where I'm going to take a sample from my distribution. This is an image of a dog, real image of a dog, and I'm going to iteratively add noise. So if you look on this diagram here, now this is not a dog, it's a person, but I'm going to go, take this image and I'm going to gradually add noise, ultimately until I get this isotropic Gaussian. Then I'm going to go through the reverse diffusion process, sample from a Gaussian, and then I work backward to get a sample ideally from the data distribution, the target distribution. And this corresponds to a Markov chain. We have this distribution Q, which is this is the forward process, adding noise. We have this reverse process, this denoising. And that's really what we would like to be able to do, is we'd like to get Q of xt given xt minus 1. Sorry, no. Q of xt minus 1 given xt. Work backwards. That we cannot get without conditioning over. So that's intractable. So we're going to approximate this with this P. And again, I'll skip through this for time. But we can get a closed form solution for this. Okay, so if there are any questions, I can take them later. But let's, I think, for the sake of time. So now, okay, so this is a diffusion model we talked about in the context of dogs, this example with faces. Can we do something like this for planning? Where now we have a distribution not over images, but it's a distribution, in this case, over trajectories of an arm. This visualizes it as the position of an end effector over time. So we're going to have a trajectory like this. This is analogous to an image, this path. Let's say I have, again, my expert demonstrations. Can I learn the distribution over those demonstrations, over tau, from, in such that I can sample from that to solve a planning problem? Then this distribution does not need to be unimodal, right? And so there's this paper by Josh Tannenbaum, Survey 11. Janitor is the first author from, the next slide, 2022, where they do this. So they propose a model called Diffuser. And it basically does planning via diffusion. And they have different variants of this. So they have their diffuser model. It takes as input, again, we're diffusing trajectories. So these are sequences of states and actions. So that's what we have here. There is this local receptive field that tries to keep things locally consistent. And then it's going to, just like a diffusion model, add noise to corrupt these demonstrations, and then learn to effectively remove noise via this reverse process. And they have different variants of this. They use this in the context of basically formulate this for model-based RL, but what we're interested in for this work is we're going to do this via basically in-painting. So if I have, my goal in this case is to reach this target. So I have an initial state where the gripper is here. My target state, so this is S0, S0. This is S capital T. And I want to in-paint a trajectory. I want to find a trajectory that in-paints between the two. That's feasible. So what I'll do is I'll basically pin. I have my diffusion model here that I've learned, distribution over trajectories with some parameter theta. I have this function h that is basically saying, well, I insist on the start being S0 and the last position being ST. And what it does is it in-paints. It fills in the states to get this trajectory. Okay? And it's pretty impressive. Right? So I'll just show some videos. This is with a walker robot. So you can see each one of these, you can see these trajectories being generated via the reverse diffusion process. The bottom is a maze navigation, so a U-maze on the left, and increasingly more sophisticated mazes. And this is showing the reverse diffusion process to generate trajectories. This is all via in-paint, where, again, I'm pinning the start and the goal, and it's filling in between. But there are some problems with diffuser. And so one is that it's not uncommon to get trajectories out that are infeasible. By infeasible, I mean in collision. So you might find that the agent goes through a wall. So we saw, to look at this, and again, this is a joint paper with Sedan, Takuma, Takaru, and Bradley. We came up with a simple maze, really simple maze-like environment. So the agent starts in one of these walls. Okay, starts in these walls here, and there's 4 goals. And the agent is randomly given one of these 4 goals. Right? So the goal is just to navigate from start to the goal without hitting a wall. So pretty simple. And so if we run diffuser on this, we find, again, not all the time, but it's not uncommon for it to output a trajectory that takes the agent directly through a wall to get to the goal. We're interested in getting a better understanding for why this is. And so one reason that we suspect is that as part of this diffusion process, the current models, the model that uses Gaussian noise, has no regard for feasibility. It's just going to, during the forward process, it's just going to corrupt the trajectory. So move state action pairs or states, depending on if it's corrupted state actions or states, irrespective of whether or not they're valid or invalid. So what I'm showing here is this reverse diffusion process. So when it does the forward process, you get the image on the left. Each one of these points is, a point along a trajectory. And you can see that some of them are outside the boundary. So again, these are walls. Some of them are in collision with these walls. And then now when you do the reverse diffusion, you remove noise. Some, again, I don't remember how far through this is, But we get these, you can see it's converging on a trajectory, but many of the still noisy samples are going through a wall.
So during training, you shouldn't be seeing trajectories that go through the wall, right? I assume you have multiple trajectories.
None of the demonstrations go through walls.
Okay, but even then, the generator.
Yeah, because when you're adding noise, you're corrupting. When you're adding noise, there's no regard for collision.
But I'm a bit confused with the training. I mean, it just seems like a failure of training. I mean, I'm a bit confused, right? You're training it to recover. You have some distribution over. You're training with the distribution over trajectories, and you're training the diffusion model.
Yes. Yeah.
So that when you reverse it, it'll look like the distribution over.
Yeah.
And this does
This
not.
is not. You're right. You're right.
So it's just
exactly.
It
You're not. Yeah. If you were matching the distribution exactly, you should not see this.
or anywhere close to it. So this doesn't seem to be a problem with the model or anything. It's straight up problem with the training. So the training is failing here.
Yeah. So we can make the training less sensitive to this, and that's what we'll talk about.
How is this different from the maze navigation example that you showed earlier, which did seem to respect the maze boundaries?
How it did seem to?
You just showed an example on the
Yeah,
previous
it doesn't
slide.
always.
Okay.
So again, to be fair, this does not happen all the time. I don't know, Takuma. Where's Takuma? Oh, there you go. I thought I saw him. How often does it happen? Do you remember?
I think it's not like super common.
It's not that common. It's not like every
But
time.
like this is a little too extreme. Like we saw some cases where like it kind of cuts through the corner of the, edges and
To
stuff.
be fair, yeah. This
So
is
you also have the problem of enforcing constraints in the maze navigation.
Yes, yeah. It's not just this. We just wanted to come up with a simpler environment where we can look at this. Okay, so one solution to this might be, well, all of these are trained, there is a data set, right? So we have this replay buffer, I want to call it that we collected. What if what I do is I just take that trajectory, and now what I do is, well, I know around here I have examples of feasible points. What if I just connect this point here, rather, the one that's in the wall, to the nearest feasible point? Right? Because these are just points along my demonstration. None of them go through the wall. All my demonstrations are perfectly valid. So what if I took that point here and I said, well, the nearest point I have, and one issue here is that, again, this might be mismatched. It doesn't actually have any demonstrations in these corners. None of the experts went there. So I would pick maybe the nearest one. Anyway, if you do this, what you end up getting is you get this clustering. All these points here are going to cluster around here. These points here are going to cluster around there, and then you're going to end up getting this disjoint trajectory. Some points on one side of the wall, some points on the other, never going around the wall.
I'm a bit confused. At what point? I mean, at what point do you do this? Like, what you say you're?
You could do this. Like, is there a simple fix to this? Could I take my diffusion model and say, well, okay, I get this trajectory. It's not feasible. Again, it doesn't happen all the time. But when it happens, is there a simple way I could correct it? I have an example when I know when I'm somewhat near here what I did, or what the expert did. So let me go look at what the expert did nearby. So for points in here, the nearest point might be here. So I'm going to do what the agent did there. And then over here, if I'm over here, I'm going to pick that point. That's closer. So I'm going to do, instead of this point, I'm going to pick what the agent did there. And so what you'll end up getting oftentimes is you get into, these points, they'll never go around.
The noise trajectory that you showed in the last slide, is that from a lot of good trajectories or from a single good trajectory?
The previous one, this one here?
Yeah.
This is from a single,
Single.
I believe. So one question now is, well, maybe we don't have to take the standard approach where we're just going to be, adding Gaussian noise. And so there was this paper from last year called Diffusion that looked at taking the diffusion model, but using structured approaches to the corruption phase, the forward diffusion process. And so this is from their paper. So each one of these rows here is a different way of doing the corruption, the forward diffusion path. So the top row is the standard adding noise, so the degradation. So we start up on the left is the original image, and then in the middle is the degraded. Again, in the case of the nominal diffusion model, that's an isotropic Gaussian, and then we go to the generated. And so they looked at things like, what if instead of adding noise, I progressively blur the image more, or I mask certain parts of the image, I pixelate, etc. Add this snow. They found that for a variety of degradation methods, you can still generate, in this case, images that look very realistic. So with this paper, and again, this is with Bradley and others, we thought, well, can we do something similar, not add Gaussian noise? Can we do what we call cold diffusion on the replay buffer? And so it's a pretty simple strategy. So when we're doing the forward process, rather than arbitrarily adding noise, we're going to, we want to degrade a trajectory, we want to degrade a sample. Again, each one is a state action pair or just a state, depending on the nature of your diffusion model. What we're going to do is we're going to replace it, not with that point plus Gaussian noise, but we're going to replace it with another point from a trajectory. So a valid point, it's a demonstration, it's state action pair from a demonstration, it's valid, it doesn't go, it's feasible, doesn't collide with anything. And that's the way we're going to do this, our corruption. And so what you get now is inherently all of your samples, all the points from the forward diffusion are inherently are not going to be in collision because you're just drawing points from this replay buffer. I don't know why that build happened that way. But again, so this is again analogous to the scenario I showed before, where in the case of the diffuser went through the walls, now it's going to go around the wall. Okay. So the approach is pretty simple. Okay, so we're going to take tau, again, as our trajectory, the sequence of state action pairs. Importantly for this, it's fixed length, so t, capital ST is the goal, S naught is the initial state. So tau t, we'll call the noise to trajectory at diffusion step t, and then we need some degradation function, we'll call that d. It's going to take as input the expert trajectory, that's tau sub 0, so 0 steps of forward diffusion, and that's going to, for t steps of corruption, give us this corrupted or degraded trajectory t, tau of t. And as I said, we have this replay buffer. And the way that we're going to do this is pretty simple. So for each state in our trajectory, so that's measures of state in the maze, what I'm going to do is I'm going to draw a ball around that state of some radius. And what I'm going to do within that ball is I'm going to take from that, so I'm going to have that ball. I'm going to take one of the demonstrated state or state action pairs that is within that ball. I'll visualize this in a bit. And then over the course of diffusion, we're going to be, just like you might be at increasing the variance of the noise that you're adding, we're going to increase the radius of the ball. So visualizing this is tau naught. This is our expert trajectory. After 30 steps, this is the noise version that we'll get. Again, all these points here are actually from valid trajectories. And then at 128 steps, we get this, this noise very noise trajectory, but all the state action pairs are feasible. Okay, so let's look at this. So we have, again, this tau naught. I'm at step 30 of the diffusion. So we look at different ways of doing the distance or the size of this ball. Linear in time over diffusion time steps or logarithmic. So we say k is equal to 30. So I look at 30, I pick my distance. I'm going to draw a ball around this point. And these little, what are they, blue? These little blue dots there are states or state action pairs from our replay buffer, from our demonstration. And I'm going to randomly pick one.
Wait, I'm a bit confused. So each time you're corrupting the previous time step, you're corrupting from 0 time.
Corrupting from, you could do it either way.
No, I don't.
So, well, you
I
can,
don't understand. I mean, what you had. Can you go back to the previous slide? What is this ball? What is S here?
S is a state, sorry, S state. So this is a state base, not state action pairs.
Okay, so what is tau?
Tau is the trajectory.
Which trajectory?
Tau is the demonstration trajectory.
The demonstration trajectory.
Yeah.
So I'm a bit confused because in the diffusion process, it's the diffusion, like the points move. They move. If you look at I don't know what you call it, forward or backward. I mean, if you go from the real thing to noise, you start from the real thing and it gradually morphs into noise. Okay.
Mm-hmm.
So, but if you look at time t and time t plus delta t for small delta t, they're very similar.
Mm-hmm.
And here it seems that t and t plus delta t are going to be uncorrelated.
You can do it both, right? You can do it both ways, Takuma.
It's still similar, right?
Yeah.
Because like we are taking a very small circle around each point, and we are sampling inside of the ball. So
You're taking a small circle around what is what I'm trying to understand.
So the trajectory consists of sequence of state, basically sequence of positions. And for each position, we are drawing a ball and sampling the.
I think what Nadi's saying is there's an iterative version, like you're always adding noise to the previous noise. You know, you start with tau naught.
So so this is
So-
are you always corrupting the initial trajectory, which is what I kind of
For
understood
that
from
question, yes, this is always corrupting the initial trajectory.
So why would the corruption at time t and the corruption at time t plus delta t be similar? Because if both of them are independent corruptions of the initial trajectory.
Oh, I see. Okay. Okay. I misunderstood the question. These two should be uncorrelated. Just that they should be still within a similar size ball.
So how is this similar? So I'm a bit confused about the analogy to diffusion processes, because this is not a diffusion process then in any way. It's not like. I mean, like a diffusion process, right? The whole point is you have like a continual thing that goes to a noisy point, then you can hope to
Well,
go back
you
to
can
the random
skip,
point.
can't you? I mean, I thought you can, right? You can do. I thought you can do like
I'm trying to understand.
q of xt plus k given xt. Right?
What do you mean you
can.
could? This is what you. This
There's
is
a,
not,
you could do a
That's
diffusion
not-
process where you
that's-
skip.
that's not what you're doing. From what
That's
I
what we're doing. Yeah,
That's not what the course.
that's what we're doing.
Wait,
This is t naught. This is so what we're doing is we're going.
I thought you said you always start from the. You always choose a point from the initial.
Yes.
So that's not what you're.
No, it is right. So what I'm saying is that here, this is going to be q of tau 0 plus I don't know whatever tau 0. This is going to be q of tau 2. Just say 2 tau 0.
Right, but if you added the if you selected tau 2 and tau 1, each of them independently from tau naught, so it would not be. I mean, this is. Are you selecting tau 1 and tau 1 and tau 2 conditionally independent, conditional on tau naught?
Yes, they are
Okay,
both conditioned
so
only
it's not
on.
a diffusion process. So it's not a diffusion process.
I mean, like tau naught and the time step, right?
And
Diffusion
the time step, sure.
And diffusion time step changes the
Yeah,
radius.
so it's not like it's not.
But it's not quite.
It's not. I mean, I'm trying to understand the analogy with diffusion
I
processes.
think it's not a diffusion process
Yeah.
in a sense that we are not
True, yes.
we are not using Gaussian noise. But at the high level, just like this cold diffusion paper, the high level idea of like corrupting the input in an increasing scale, in that sense, it's a diffusion process. I mean, that's what the cold diffusion.
What you're not getting is sampling xt plus k and xt plus k plus 1 correlated.
Yeah, that's what.
You're not doing
Mhm.
that's standard in the diffusion.
Yeah. We could do that as well. I mean, with this approach.
They were correlated. If you're calculating xt plus k plus 1
Yeah.
from xt plus k.
But I'm saying we could do that rather than doing this, this jump.
I mean, that's a completely different. It would be a. I mean, again, that would be a diffusion process,
Yeah.
whereas this is not a diffusion process. And so, in particular, I mean, the diffusion process. I mean, there's no hope of learning a backward. It's no. I don't understand what the backward process here even means, right? In this case, I mean, there's no, because it's not a. Okay, at least I understand now what you're.
Okay.
What I understand what you're doing now. but
We
so-
could do it both. Yeah, we could do it both ways, but this is how we did it. Okay, so see. Okay, we saw this. So yeah, we have this ball. And then we have this reverse process, which is doing this restoration. This we just model as a neural network.
No, so this is what I don't understand. So what is the reverse process? What is it trying to, what's the reverse process here?
I mean here, so okay, so we have, this is our degraded initial trajectory. So T naught, T is 0. This is T diffusion steps. Excuse me. And then this is again t of 0. And we want to train this neural network that minimizes this L2 loss between the state in this case, or sorry, state sequence because it's a trajectory, or state action sequence. We looked at both. Between the t of 0, so the expert's trajectory, and our noised trajectory. So it's going
Okay.
directly back.
Okay. And then what? And then what do you do with it?
That's what we did. That's what do we do with it?
Suppose I have this r theta. How do I use r theta?
We use that during the reverse process to generate a trajectory.
You give it like a bunch of very noisy trajectory and then you ask it to iterate to do
Yeah, so so it's given noise when we're training it giving noisy trajectories, right? Right? Does that make sense? So this is a noise. This basically after 30 steps is something like this. So there actually is a trajectory in here. These are all just the points, but there are several candidate trajectories in here. And then we train this, again, this is a network, we train this to reconstruct. Okay, this isn't the demonstration, but you can imagine the demonstration looks similar. We train it to reconstruct. Well, actually, maybe this visualization is the demonstration.
So could you just constrain r theta so that it cannot output a prediction that overlaps with the invalid region?
Yeah, you probably could do that too. I don't know. You might again have some phenomena where you might, again, I don't know, you might get, I can imagine you might get the same clustering behavior that I mentioned before. That, because of the forward process, my noised point was in here. And now I'm trying to minimize the distance to a point in my trajectory. I might just connect it to this point. I might, get a bunch of points around here and a bunch of points around here might not learn to go around. Does that make sense?
There's a connectivity constraint you also need to.
They could, yeah. I don't know. I can imagine that happening, but I don't know for sure. Gene, you had a question?
Yeah. So in this loss, because the middle picture is not really. So you're just training it on the first and the last one, right?
We train it on. We train it on all.
On the middle and
What's
the
it?
last. So the loss is like a sum of the first and the last, and the middle and the last.
At various points along the way. This is just, I'm just visualizing 2 points, or 3, I guess. This is k is equal to 30, but this is k is equal to 128. But we're doing it at each point in between.
It is true that in a diffusion model, even though you're training two adjacent states, the target of the training is the original image. You train toward the original image. It's a weird fact about.
No, that's true. But here
he's training toward taking a state and training toward the original image.
I still really don't understand how the intermediate time steps. I don't understand how r theta is actually. Suppose I trained r theta. I still don't understand how do I use r theta. Do I just use? Do I just use it for t
So
to 0?
in a classical diffusion model, you take one little step in the direction of the original
Right.
image.
So I keep doing a lot of little steps. But here, all the steps jump to the end. So
No, he's got an intermediate step in the reconstruction.
The reconstruction has intermediate steps.
you're not training on that. You're just training on the final
But
step.
that happens in a diffusion model too.
No, diffusion of the objectives in the last one. What you're training is how to do a small
You
step.
train toward the last one.
You train
For
your
the
objective is in the last one, but you train how to do a small step so that your last step will be good. Here you're just training how to do a big step.
We should take this offline.
Okay. How are you using r theta? I guess I don't understand. I trained r theta. Great, I have r theta. How do I use it now?
So now I train our theta. I have I pin my, in this case it's just states. We're not doing, well, we did both, but let's just say states. So S naught is the start, ST is the goal. In the beginning I have random points from my replay buffer,
Okay.
and then
So you choose it in the random point. A trajectory consists of random points from the replay buffer.
Yep.
Okay.
or is it random or is it uniform over the for the sequence states? Is it uniform when we start the reverse diffusion process? Is
So
it
start and
uniform?
goal are pinned,
They're pinned, yeah.
and others are just sampled uniformly.
Uniformly, yeah,
Okay.
okay.
And
So we
then-
start uniformly,
And then
and then I apply this reconstruction for
okay.
each step. T is equal to 128, T is equal to 127, T is equal to 126.
Well, all the time from the initial one.
When you initially you mean T naught or you mean the noise?
The random.
No, the right,
I don't
no.
know. What do you apply them to?
Right, I mean, we go from tau of,
You just learned how to go from some positive t to 0. That's the only thing you train on, right?
So-
okay, I
Yeah.
think we can go.
Okay.
We can maybe talk this later. I mean, I still don't understand how
okay,
this is.
so, okay, so we looked at this again, this maze environment, maze tight, has narrower gaps, and a couple fetch manipulations. So pick and place with an obstacle or this wall, so pick and place, pick something, place it, there's a wall in between, reach with obstacles, etc. And so we look at various methods. Diffuser is the one that I talked about before. And a behavioral cloning version. QL is, I think, a recent paper I showed on Song. And then our method. And again, for maze diffuser works pretty well. But when you make the border tighter, then it ends up clipping corners or it ends up in collision. So again, that one image I showed was admittedly a cherry picked. But we find that this pretty simple strategy where you're just, as part of the forward process, you're just corrupting two feasible points works surprisingly well. Not the best, it's not perfect in some environments. And again, we're not guaranteed that the points that we get out are collision free. It still is possible for it to collide, but it happens far less. Okay, so really don't have much time. Just a visualization of some of the trajectories for diffuser and our method around an obstacle. Theirs is in collision. Okay, so next, and I'll try to be quick. So this, again, the idea is that from our demonstrations, we have these multimodal trajectories. One person decides to go left at the fork in the road, one person decides to go right. And what we would do what our policy would do is it would emulate this distribution over this expert behavior. But what if, we want some level of agency. So I don't want a self-driving car. I'd like to be able to get in the car, but I'd like to have some independence. I'd like to be able to take this car on a racetrack and drive. But, I'm not a race car driver, so I would like the system to help me so that I, maintain some level of safety. Say, for example, drive like I am an expert race car driver, but with, feeling like I'm in control, not necessarily go and letting it take over. And we've done this for manipulation as well, and this is something we formulate, or is formulated as what's referred to as shared autonomy. So we want the user to have some level of control. So again, what we're going to assume is we have some demonstrations of desired behavior. This distribution of desired behavior may be multinomial. And the question is, if we knew, or we had a model of P desired, could we use this to guide the user? And how might we get this? So we're going to use diffusion models to get this. Now, we've already talked about diffusion model, but a full diffusion model, if you imagine going, forward to zero mean isotropic Gaussian noise back, removes all notion of agency. And I'll say a little bit about what they mean. That's one. And the user's goal, may be latent. Again, going back to this Muppets example, it might not be clear whether I want to the left at this fork of the road or the right, or left around that traffic cone or the right around the traffic cone. The policy, if I use a standard diffusion model, is just going to pick one of these. I'd like to be able to have some notion of control. So one way you can visualize this is with this notion of this plot. So what I'm showing on the bottom is this forward diffusion ratio. So full diffusion goes, imagine the input is the user's steering and gas. I'm going to add noise until I nominally get a zero mean Gaussian. Then I'm going to reverse the process. So what I'm going to get, so that's alpha is equal to 1. And so what I get out of that is, not this performance. I'm going to conform to my demonstrations. Right? I'm going to get, a real image of a dog, irrespective of maybe what I would like it to look like. And we get a sample from this distribution. So high conformity, we're going to say low fidelity because it's not adhering to what the user wants. The other end of the extreme is that we don't diffuse at all. We get the user's input. I'm driving the race car, but I'm not a race car driver. Good chance I'm going to crash. It's high fidelity, but it's not conforming to the policy. Okay, so let's visualize this. So imagine on the left we have our demonstration distribution. There are 3 modes. These are different driving behaviors, or in this case, lunar lander, different ways of flying this drone. When I go through the forward process, I'm going to keep adding noise, anomaly in the limit. I'll get an isotropic Gaussian. Then I'm going to reverse that process. Let's say the user's distribution is something like this triangle. And again, this is driving behavior, flying lunar lander. One of these modes might be landing, one might be just hovering around, maybe another one is going to a different goal. My policy, I have some points over here, they're not feasible or they're going to crash. If I do full diffusion, so completely add noise, get this isotropic Gaussian, and then reverse diffusion, I'm going to get a distribution like this. But my point that was up there that might have been trying to just hover around might get diffused to a point down here that's going to land somewhere. Or that's going to go to a different location. What if, instead, I did partial diffusion? So I'm going to take my user input, I'm going to add some noise, but I'm not going to go all the way to an isotropic Gaussian, and then I'm going to denoise it. So we have this switching that's going to tell when we're going to switch from forward diffusion to reverse diffusion. Another way of visualizing this is that this is a recent paper that we just somewhat recently became aware of, called SD-Edit. Some of you might be familiar with this. It's a pretty cool idea. So again, going back to this picture of a dog. Let's say I want a picture of a castle, but I don't want just a random picture of a castle. I have a sketch. So what I do on the left is I sketch a picture of what I want my castle picture to look roughly like. Right? And so if you look at this, here's my distribution. Here's my distribution over images. This is, again, analogous to the policy. In this case, it's 2 modes. The previous example had 3 modes. Here's my stroke. They're complete. There's no completely disjoint distributions. And so what I'm going to do is I'm going to add noise, and we control the way I add noise to this stroke distribution. Basically, spread the distribution out. So now there is support. And then I'm going to denoise it, and what I get is a sample, a real image of a castle that resembles this sketch. And there are a lot of other cool visualizations in the paper. Can we do something similar where, again, it's not sketches, but I'm applying some gas and brake, I'm steering the car to the left, but I'm going to get a sample for my distribution, the expert policy that's consistent with going to the left, but not crashing. Right? And so that's what we do. So we do this on 4 domains, this lunar lander, this block pushing domain, and then this goal is to be controlled, but I'm not going to talk about that. And we look at doing this with a variety of different pilots. Some interesting things with this. All we need are expert demonstrations. We train a policy to emulate our expert. And we try this with different, that's the co-pilot, and we try this with different pilots for a lunar lander. And we see that the method does well. What are we looking at? We want high success rate. So a lunar lander, the goal is to land between these flags. The co-pilot that's helping me doesn't know where I'm trying to land. Only I know. Only the pilot knows. Or in Lunar Reacher, I'm trying to reach this red ball. I know the ball I'm trying to reach, but the co-pilot doesn't. And so they're taking as my input, and I'm going to do this partial diffusion. So the question is, how far do you go? 1 is full diffusion, 0 is no diffusion. We do 0.4, this hyperparameter. There's a whole sensitivity analysis in the paper. We find that it's actually really surprisingly robust. Like for various different types of pilots, like you or me, 0.4 is a good value for these domains. Right? Okay. Yeah.
Just to make sure I've understood it. So the task is either land on the ball
Oh,
or between the two.
Yeah, so there are 2 different games here.
Okay.
One is lunar lander, where you want to land, and the flag position changes. It's random. The other is lunar reacher. I think that's what Chip came up with for another paper we were working on, where you have this ball, and it's placed randomly in the environment. Your goal is to fly to it.
I see. So when I use the assistant, the co-pilot, it's up to the user to know whether he or she wants to place it between the two flags or the bottom.
No, so these are two different
Oh, these are
tasks.
two
One, you'll be given,
Oh,
you're
I
the
see.
flag, your job is to land
I
the
see,
flag.
okay.
The pilot, the co-pilot, it doesn't, I think, I'm trying, it doesn't know where the
I
flags
see,
are.
okay.
And some of the pilots maybe just hover in place.
Got it.
So they're not all the demonstrations are landing. So it might be that you want to play the game, you just want to fly around, you can do that as well. Okay. So we did this, again, with these simulated pilots. We also did this with people. I don't remember how many people, maybe 20, 30 people. Thanks to Lucha, who I think did a great job recruiting people. And we had people play this, and we find that the behavior is similar. Again, we want to compare with and without the co-pilot. And people are far more successful, crash far less when they're using, more successful when they're using our co-pilot. And we asked them, survey questions, what did you think about how much level of control you had, how collaborative was it, et cetera. And they preferred having a co-pilot, our method, versus just trying to play the game. And if you play these games, they're hard. We also did this on a real robot, so we have this very toy, simplified towers, not really towers of Hanoi. We have two pegs, and the goal is to stick this cylinder, in this case electrical tape, on one of these goals. The co-pilot doesn't know. You're told when you're playing this with this joystick, put it on the one on the left, or the one on the right in your perspective, or person's perspective. And more successful. It's not a terribly hard task. I think they can play as long as they want. It takes a while, can take a while, because we're not looking at the robot, you're looking at this video feed. But using our co-pilot, it was more successful, 10% more successful, and the trajectory, so the time was lower. Okay, so just very quickly, the last bit. All of what I talked about assumes that these demonstrations that we have are from experts or near experts. What if our demonstrations are not of an expert behavior? Okay, so now what we want is, our goal is not to get a policy that performs similar to these demonstrators, but actually maybe performs better. There's a lot of work in imitation learning from suboptimal experts. And one domain that we're looking at is this ant maze. So this is looking down, 5 minutes? Okay, perfect. Looking down, you have this maze-like environment. There's this ant, and many of you may be familiar with this ant from OpenAI Gym. And so, actually, let's see, here it is. And so the goal now, the action space is joint torques. So 4 legs, two joints per leg, so 8 torques that you're controlling. And it's, ant is relatively easy to maintain, keep stable, but not, this will flip, so it's not perfect. And now your goal in this is to control the legs of this ant so that it navigates from some random start location to a random goal location. And we have demonstrations of this. This is from the D4RL data set. And if you look at running behavioral, and there are versions, different sophistications of mazes, different types of demonstrations. So U-maze is a small maze, medium is medium, large is large. And so for the simple U-maze, behavioral cloning works reasonably well. 50% of the time it gets there. But once the mazes become larger and the demonstrations are actually poor, that's what diverse means. Diverse means behavioral cloning just fails. It's just too hard to stumble, essentially, or too hard to emulate, to come up with a valid policy. And this is actually hard for RL as well. So none of this, again, up to now, there's no reward. But, this is a sparse task. So my goal, again, is to get to the goal. When I get to the goal, the learner gets a point. Doesn't get any reward signal otherwise. And so if you try training, like, say, soft actor critic on this, it fails because it's just, because of the credit assignment problem. I think there's a visualization here, yeah. So exploration is hard. And so is there a way we can use these demonstrations to solve these sparse reward RL tasks? And can we do that by coming up with better exploration policies? And so there's 2 different ways of dealing with this. One is just, I'm going to densify the reward. Forget about the fact that I only get a point at the end. I'm going to give the ant points for getting as it gets closer to the goal. That's maybe one approach. But can we actually learn subroutines that make this exploration more abstract? So rather than exploring over low-level actions, I'm going to get these short trajectories, if you will, and so basically my action space becomes much smaller. Credit assignment is a lot easier. That I can learn to do exploration. And you imagine like, navigating a maze, maybe not with the ant, with a ball, I might just repeat, a lot of the actions we're executing I repeat, right? I'm gonna go forward for some period of time. If I just stitch those together and I call that one action, that might work, not for ant. Okay. So this is the language-ish part. So this work, again, I'm gonna go through this quickly because I'm out of time, but what we're going to do is we're going to take it, we're going to model this after the way that language models use subword tokens, particularly byte pair encoding. So running, for example, might be composed of run and these subwords run and ing. And so byte pair encoding, the way that it works is pretty simple. We start with some string, shown here, with some vocabulary. And what I'm going to do is I'm going to look for frequent words. In this example, AB is repeated. So I'm going to replace AB with a new subword. In this case, I'm going to call it X. So I'm going to merge them, and now I get this new string. Then I'm going to repeat this. I'm going to say, well, now are there repeated words here? I guess there aren't in this case, but maybe there were a couple XT. So I might combine those and say, oh, that's a new subword, etc. And we're going to keep going until we get the desired vocabulary size. And so one question is, can we use this for RL? And so this is the way we're going to do it. We have our set of demonstrations.